Okay, so I'm going to continue where Professor Weinberg left off. And one thing I just want to say is that one of the reasons why modern progress has been possible is because of a rather technical issue, but it turned out to be very important, which was dimensional regularization. Because this was a regulator which respects gauge and chiral symmetries as well as dimensional analysis, and it made many results much more clear. Since Professor Weinberg didn't have slides, I just wanted to show you his famous formula, which he mentioned in words, which was how the power counting formula for chiral perturbation theory, which tells you that amplitudes grow like a power of momentum, and the momentum formula is given by this over here. So every time you add a loop, the power of P goes up by 2. And really the modern era, I think, started with this paper in Physica, which showed how to calculate loops in chiral perturbation theory, how to renormalize the loops, and that the non-analytic parts were related, were fixed by unitarity, and which is related to some earlier work by Lee and Pagels. Based on that, there was the famous series of papers by Gassel and Lloyd-Wheeler doing chiral perturbation theory at one loop in a very systematic way. As a graduate student, I learned EFTs from Howard Georgi's. I mean, they're really, I think, quite a brilliant set of lecture notes, which became his Weak Interactions book. And Steven Weinberg was still around, and before he hadn't gone to Texas yet. Mark Wise was there as a postdoc. And at least my impression was that what we consider modern EFTs when I was a student were considered ancient standard stuff, which we were all supposed to know and use. And so I'll explain some of the concepts. And really one of the reasons for EFTs, which is widely separated scales, arose because of the famous calculation of the gut scale, because of the renormalization of the couplings, which suddenly pointed to a much higher scale than we were used to thinking about in physics. I mean, when I was a student, people thought maybe the top quark weighed 10 GeV, maybe 20 GeV. That was the limit of what was considered very heavy. And 10 to the 15 GeV is a huge scale. Okay, I'm going to skip his history. And essentially, the modern era, as far as I'm concerned, deals with how to do loops in a systematic way. And because of that, you can then apply EFT methods to many problems. And as I said, the talk's not going to be a review. The subject is huge. There are many applications in condensed matter physics and gravity and cosmology. And I'll cover just a few topics I've thought about. There'll be many more talks in the series. And so I'll give a brief overview of a few slides on some of the main EFTs that in particle physics. So let me first start with just a regular quantum field theory. So a regular quantum field theory has some Lagrangian. I've taken a scalar field coupled to gauge fields. And the interesting terms are the gauge interactions and lambda 5/4 couplings. And these are all terms of dimension 4 in the Lagrangian. But there are two interesting terms here: the cosmological constant, which is, the operator is dimension 0, the coupling lambda is dimension 4, and then the mass term, which is dimension 2. And the Lagrangian implements the symmetries of the theory, that is Poincare invariance, internal symmetry, gauge invariance. And I think a very important aspect of EFTs and QFTs in general is it includes locality. And this is what Weinberg in his talk referred to as cluster decomposition. And it's the only way we really have of implementing relativistic invariance and locality in a systematic way. So just giving the Lagrangian is not good enough, because if you start calculating, you get infinities. And so regularization and renormalization are part of the definition of the theory. You just have to consider that as like a footnote or a subscript on the Lagrangian, which tells you how to calculate. Now, if you're given the Lagrangian I wrote down, which has operators up to dimension 4, you can compute everything, at least in principle, including non-perturbative effects, if you have a renormalized theory. But in practice, there's always some small expansion parameter or some approximation being made, because you can't generally get exact results. Even in lattice calculations, there's some fixed numerical precision, some finite size effects, etc. And even if you could calculate to all orders in perturbation theory, there's a whole interesting subject. The perturbation series is divergent and related to non-perturbative effects. But typically, we never have exact results in field theory, except in some very special cases, typically in 1+1 dimensions. So the way I view the QFT is that the parameters in the Lagrangian aren't really any fundamental things. They depend on regularization and renormalization schemes, and they're intermediate calculations at quantities which are useful for calculations. So for example, QED has two parameters, which I'll call alpha and m of mu, which have put the mu there explicitly to kind of indicate that they're not really experimental quantities. But the point is that with two parameters, there's a whole host of experimental quantities you can calculate. And you use two of them. I've chosen the first two as inputs to determine these intermediate parameters, and then out come all your predictions of the theory. So as long as you have more predictions than inputs, I mean, more measurable quantities than parameters, you have predictions in your theory. Now, the basic idea of EFTs is kind of obvious in some ways, that you do not really need to know you don't need to know the exact short distance theory to be able to compute long distance quantities with high precision. Sort of a sound bite is you don't need to know about quantum gravity to build a bridge. And we sort of use this concept all the time in everyday life and in physics. The setup I'm going to use is there's some large energy scale m, and we want to calculate in our theory at momenta which are small compared to the scale. So the approximation is going to be in powers of p over m. Often this thing is called lambda, but I'm using lambda for the cosmological constant, and I hope I switched all my lambdas to m's here. So the EFT can be used as an expansion in powers of p over m. And one of the things when you have a ratio of scales like this, when you start doing loops, is you get logarithms of the ratio of scales. And if p over m is a tiny number, logs of p over m are large. And if you have a coupling constant, alpha times a log no longer has to be small compared to 1. And what the EFT does is it allows you to resum all of these logarithms and get a calculable finite, restore the validity of perturbation theory. So this is called renormalization group improved perturbation theory. So let me just summarize some of the, quickly, some of the reasons for using an EFT. So first of all, every theory essentially is an EFT. We don't know the exact theory of nature. We are always has some unknown stuff we're neglecting. The other thing it does is it greatly simplifies the calculations by only including the relevant interactions for the process that you're interested in. What EFT you use depends on what observable you're going to calculate, and you have to figure out what the appropriate EFT is for what you want to do. And figuring out the correct EFT is not necessarily trivial. It can be very complicated, very non-trivial and non-intuitive to figure out. Technically, the reason it's useful is you deal with only one scale at a time. If you do Feynman diagrams with multiple scales, you get horrible complicated functions of all the ratios of scales. But if you just have a single scale, there's no dimensionless ratio you can make. And so you don't get any functions, you just get constants, and that's much easier to calculate. The other interesting thing is that it makes some symmetries manifest. So QCD has hidden symmetries. There's a chiral symmetry which is spontaneously broken, which leads to pion interactions, which Professor Weinberg talked about last week. Heavy quark symmetry has heavy quark theories have spin flavor symmetry, the so-called Isgur-Y symmetry, where you can exchange B and C quarks or flip their spin. It doesn't really matter which quark it is, because if it's very heavy, it's just sitting there at rest. And all of these are not manifest in the QCD Lagrangian, because QCD describes all of these simultaneously. But if you take special limits, it's, for heavy quarks, the spin flavor symmetry is important. For light quarks, the chiral symmetry is important. And going to the EFT focuses on one kinematic regime at a time. And so the EFT Lagrangians have these symmetries explicitly in them. Then summing logs is what I was talking about when I was referring to renormalization group improved perturbation theory. So just as an example, the strong interactions The strong coupling at the B quark mass scale is about double that at the Z scale because of renormalization group running. And in the electroweak theory, the way you sum these logs is that the logs arise from ratios of MW over MB. But if you go to the effective theory below the weak scale, you essentially convert MW you take MW to infinity, and so they get converted into logs of mu over MB, and this is what the renormalization group sums. And so running the couplings in the electroweak, in the low energy theory below the electroweak scale allows you to sum these logs. And similar things happen in all the other effective theories that I'm going to talk about. EFTs are an efficient way to characterize new physics. If you start to see certain deviations, a very nice way to figure out what's going on is to just write down the most general possible operators that you can have and then figure out which operator is causing the deviation. And then maybe you get some clue as to, in which direction to search for new effects and new ideas to explain the deviations. A very important thing which was done in heavy quark effective theory is we could include non-perturbative effects in a systematic expansion. So there are non-perturbative effects in BDKs which go like lambda QCD over M. And in heavy quark effective theory, there are two non-perturbative parameters, lambda 1 and lambda 2, which are of order lambda QCD squared. And you get effects proportional to lambda 1 over MB squared and lambda 2 over MB squared. Now, the reason I'm emphasizing this is because it's a field theory. These are well-defined, renormalized operators. They have a precise definition. And you can use the same parameters in inclusive BDKs, form factors, a whole host of places. And they have the same value in all of the places. And you couldn't do the same thing if you had some kind of model of the non-perturbative effects. OK, so now let me put a few equations about the EFT. So the key concept for the EFT Lagrangian, again, is locality. And so what we do in an EFT is you just take our usual field theory with dimension operators with dimension less than or equal to 4, what people call renormalizable theories, and just keep going. You add operators of dimension 5, and they're suppressed by some high scale M, O6 by M squared, et cetera. And in some sense, you can think of 1 over M as the Compton wavelength of some high scale particles you've integrated out. Or you can just say, well, I don't know what's going on at the scale M. I'm just going to parameterize it by this. But we have a local Lagrangian at the low energy scale. And I'm going to calculate it momenta small compared to this. So it's worth emphasizing that an EFT is a theory. It's a field theory. You're given the Lagrangian. And once you're given the Lagrangian, you use the Lagrangian and you calculate. You do not have to know anything about the theory at M. You don't need to do anything outside this Lagrangian. You can calculate with this Lagrangian just as you can with the QED Lagrangian. And the only subtlety, if you want, is that you have to treat this as an expansion in powers of M. You shouldn't try and sum up the 1 over M terms like some kind of geometric series or whatever, because then you will mess up the EFT power counting, which I'll discuss soon. The parameters in the EFT Lagrangian are determined by low energy experiments, and effects of high scale dynamics, which are not suppressed by powers of M, can all be absorbed into shifts in the low energy coupling constants. And the procedure of doing this calculation is referred to as matching. OK, so I've referred a couple of times to power counting. So the way this works is that if you work at a certain momentum P and you have some operator which has some powers of M in the denominator, then by dimensional analysis, the amplitude is going to go like P over M to the D minus 4. And it's D minus 4 because the powers of M in the denominator are shifted relative to the dimension of the operator by 4 because the Lagrangian has dimension 4. So if you're willing to tolerate some non-zero error, a non-renormalizable theory like an EFT is just as good as a renormalizable theory. There's no real difference as far as using the theory is concerned. If you are willing to tolerate a finite error, which means some finite exponent here, let's say I'm working to order P over M squared and neglecting P over M to the 4th, There's only a finite number of coefficients, and you can just calculate and get predictions which are parameter free. If you want more accuracy, you can improve the precision. To do that, you have to go to higher dimension in this power counting expansion in P over M, but you also have to go to higher order in just regular perturbation theory in alpha S and so on. The usual renormalizable case is sort of the limit of this, where you take M goes to infinity, but you still have the alpha S and other expansions that we're doing. So, so there's really, at this point, I would say that, you know, the two, from as I said, a non-renormalizable theory, you can just use it just as you would a renormalizable theory. There's really no difference at this point. So in the standard model, what happens if you start with d bigger than 4? So the analysis I was talking about deviations was from the standard model was done a long time ago. And by classifying the operators, Weinberg, Wilczek, and Z showed that the first operator was a dimension 5, and it violates lepton number. And it's this operator. There's a unique operator up to flavor structure. And it gives a Majorana mass to the neutrino, which if the VEV, the vacuum expectation value of the Higgs fields are sitting here, is 246 GeV, the mass goes like the VEV squared divided by a power of M. And so if you plug in the naive values of the neutrino masses and just assume this constant is order 1, you get a very high scale, the so-called seesaw scale of order 10 to the 15 GeV. And we have seen, sorry, I shouldn't say Majorana, we've seen neutrino masses. And I think it's very important experimentally to check that lepton number is violated by neutrino masses. And I think that series of experiments is one of the most important fundamental experiments underway. And they should, okay, my expectation is they should find lepton number violation, but I'm a theorist and it's always good to have an experimental test of what's going on. The other result from these old analyses was that the first baryon number violating operator was dimension 6. And so this gave a very natural explanation for why baryon number was conserved or approximately conserved and the proton lifetime was so large. It's suppressed by some very high scale. And again, if you take the experimental limits on proton decay and figure out the scale, you again get something of order what's called the gut scale of order 10 to the 15, 10 to the 16 GeV. Okay, so I've sort of been working at tree level, but what about loop diagrams? So if you take loop diagrams with some insertions of these higher dimension operators at these two vertices, a loop integral depends on the external momenta and all the particle masses of things running around the loop. But by construction, we're looking at a theory where all the particle masses and all the momenta are small compared to M. And the key point about dimensional regularization, which is what makes this analysis simple, is that dimensional regularization does not introduce any powers of a scale mu into the calculation, only logs. So directly by dimensional analysis, if you have powers of 1 over MA and 1 over MB in the numerator, what you can get in the denominator, all you can get in the numerator are low energy scales. And therefore, a graph like this automatically has an amplitude, which is of order 1 over MA times 1 over MB with something on the top to make up the dimensions, which is the momenta P we're worrying about. So this is what I mean by manifest power counting. You just add up the inverse powers of M. If you had 20 vertices, you just add up the powers of 1 over M in all of those vertices, and that's the order of the graph. If you look at the old chiral perturbation theory literature, when you start doing graphs like this, you get where things were done with cutoffs, you got powers of cutoff, and you had to realize that that was an artifact of the regulator and figure out how to subtract it. But with dimensional regularization, all of this is easy. And so this is, anyway, so this is the power counting of the EFT. So you immediately get the power counting formula, which is the analog of Weinberg's power counting formula for a general EFT. That is, if I put graphs together with various operators, d minus 4, because the power of 1 over M is d minus 4 for the relative to, for an operator of dimension d. D minus 4 is just the sum of D minus 4s for all of the vertices in the operator. So that power counting formula tells you that there's only a finite number of terms to order 1 over m. And if I work to order to 1 over m, I would get one insertion of dimension 5. If I work to 1 over m squared, I would get one insertion of dimension 6 or two insertions of dimension 5, etc. And this is completely equivalent to Weinberg's power counting formula. Here I'm counting powers of m in the denominator. In the chiral case, Weinberg counted powers of p in the numerator, but by dimensional analysis, the two are related. So they're really, you can go from one to the other. One reminder to people working on this, if you start truncating your expansion, like in the EFT, you stop at dimension 6 and throw all of this away. The operators are still there, whether you write them or not. So for example, if you do a loop graph with two insertions of dimension 6, you'll get a divergence at dimension 8, and you have to put the counter terms and the renormalization pieces there. So even if you would like to drop them, you can't, they're there. Okay, one thing I did when, this is what my thesis was on, was something which Howard and I called, Georgia and I called naive dimensional analysis, which was basically a scheme for keeping track of factors of 4 pi in addition to the scales. And this was based on Weinberg's earlier work of counting 16 pi squareds in loops. And we came up with a method which works for basically any field theory, which is given here, where you distinguish between lambdas and f's, which are related by 4 pi. And I won't go through the details of the power counting formula, but we have a result like this. And this was relevant for chiral perturbation theory because f pi, the pion decay constant, is about 100 MeV. And the reason chiral perturbation theory works is the scale of chiral perturbation expansion is not f pi, but 4 pi f pi, which is about a GeV or 1200 MeV or something like this. And these 4 pi's make a big difference when you start estimating coefficients. So for example, in the EFT, you get a bunch of operators and the 4 pi factors go from 4 pi to the plus 4 to 4 pi to the minus 2. And 4 pi to the 6th is 10 to the 6. So your naive estimates of the size of coefficients can vary by 6 orders of magnitude if you put in the 4 pi's versus not. Okay, so now I'm going to come to something which is going to get me into trouble, but I'm going to say it anyway. So in the standard model, there's an operator of dimension 2. So Steve Weinberg mentioned this last time. It's the Higgs mass. And there's one of dimension 0, which is the cosmological constant. And we've been talking about power counting in inverse powers of m. What do you do with of the high scale capital M? What do you do with these two operators? Well, if you try to apply the naive power counting argument, you would say, well, the Higgs mass should be of order capital M squared, and the cosmological constant should be of order capital M to the 4th. And just to pretend that capital M is like a gut scale of order 10 to the 15 GeV. Well, this is a disaster because the Higgs mass is 125 GeV. And the 4th root of the cosmological constant gives a scale of 10 to the minus 3 electron volts. But this is, as I said, an unthinking application of power counting. So let's go back and just repeat this analysis, but we're going to treat the standard model as an EFT at the electroweak scale, where so at the scale V, and M is much larger than V. By assumption, we're dealing with a theory which is valid at the scale V, and all the particle masses are at or below the electroweak scale. So we should take the Higgs mass to be of order the electroweak scale. If it isn't of order the electroweak scale, we had no business writing down the EFT in the first place. The particle wouldn't be present at the electroweak scale. So is this consistent? Can we do this consistently in the effective field theory or not? Well, if you start looking at loop effects in the EFT, you will find by dimensional analysis that the corrections to the Higgs mass go like coupling constants to powers times the Higgs mass squared. Or they go like m Higgs to the 4th over big M squared times coupling constants, etc. But you never get powers of m in the numerator, just by the way the theory is constructed in the structure of loop diagrams. So if you start with the EFT where the Higgs mass is of order the electroweak scale, there's no inconsistency. All radiative corrections are of order that or smaller. So there's no fine tuning you need to do to hit M Higgs in the EFT to keep it light. Another thing this always bothers me is people keep talking about quadratic divergences by drawing graphs like this and arguing that these graphs are of order the cutoff squared and this is responsible for the hierarchy problem. If you actually do the integral, you find that there's no contribution of order cutoff squared in the dimensional regularization. This graph is proportional to the Higgs mass squared, and there's no big scale coming in. So I think that people trying to get rid of quadratic divergences of the electroweak scale are trying to solve the wrong problem. The real problem, which was the way this was phrased originally, I think, was that if you have a more fundamental theory, such as a unified theory, how does that theory dynamically generate two widely separated physical scales? And by physical scales, I mean some particles like the W and Z, and some particles like X and Y bosons whose masses you can measure, and they're separated by orders of magnitude. And I think this is a totally different problem than figuring out how to construct a theory where you don't have to fine-tune parameters of the Lagrangian order by order in perturbation theory and things like that. Nature doesn't use perturbation theory. It doesn't really matter what the Lagrangian parameters are. They're not observables. And even a lattice calculation, you have to fine-tune the Lagrangian to get to the scaling point so you can do calculations. Now we come to the dimension 0 term, and this is a little bit different from the Higgs, because if you start doing calculations, you might get corrections. Well, the bad one, since I don't want to spend too much time or I'll run out of time, is you get corrections to the cosmological constant of order the Higgs mass to the 4th power times coupling constants. So even if you had an EFT at the weak scale, the cosmological constant is a huge problem, because even in the low energy theory, the size of lambda isn't natural. Higgs corrections or QCD corrections give corrections to the cosmological constant, which are many orders of magnitude larger than the experimental value. And right now, the only solution we have to this problem is anthropic. Okay, so this is sort of the first part of the talk. And then the second part, the organizers want me to quickly discuss some of the various EFTs which have been done, people have worked on recently, and there'll be a whole series of talks on, with many more technical details on each of these. So I'm just going to give like 1 or 2 slides on each of them and then discuss some things I thought were interesting. So the first EFT, okay, and some of these are sort of have a different footing, and I'll try to, from what I've discussed before, and I'll try to explain. So heavy quark effective theory discusses the interactions of heavy quarks like B quarks and C quarks with light degrees of freedom. So that, for example, a B quark bound in a B meson where it's interacting with light quarks and gluons. And the key idea here was to write the momentum of the quark, factor out a big part, which is MQV, and call K something which is called the residual momentum. And the reason for doing this is the first term is of order the mass of the quark, and the second term is of order lambda QCD and much smaller than MQ. And so you're going to do an expansion in powers of K divided by MQ. And you can just think of this as going to the rest frame of the quark where the velocity is 1, 0, 0, 0, and then this just removes M from the energy. And if you do this, you get fields which are labeled by the velocity. And the heavy quark Lagrangian, when you write it down, has the spin flavor Isgur Y symmetry manifest. And some new features which arise in this theory are that anomalous dimensions depend on the velocity because the fields have labels of the velocity. And I mentioned this earlier, you can do include non-perturbative effects systematically via higher dimension operators like this, which lead to non-perturbative parameters lambda 1 and lambda 2 and so on. And this theory has been used extensively to extract MB, the CKM angles. I mean, there's a whole host of phenomena that you can do. But the key difference from the old theories is you also have this little label V to deal with. The idea of velocity dependent fields was used in chiral perturbation theory for baryons, the baryon mass is order of GeV and therefore not small. And so you couldn't do just chiral perturbation theory naively because you would get factors of m nucleon over 4 pi f, which is 1, and would lead to a breakdown of the expansion. But by using velocity-dependent fields, it turns out that you can ensure that the expansion goes back to the usual expansion for pions and powers of m pi over 4 pi f, or small scales over 4 pi f, and you never get powers of the baryon mass in the numerator. In fact, the analog of the heavy scale in this case, you get powers of 1 over the baryon, inverse powers of the baryon mass. And there's a very nice connection of this with the large N expansion, because in the large N limit, baryon masses are order N color and go to infinity. And so this 1 over Mn expansion in baryon chiral perturbation theory is combined with the 1 over N expansion. And we were able to get some very interesting results on the spin flavor structure of baryons. And so just as an example, we could prove that the F to D ratio in the baryon magnetic moments is 2/3 plus order 1 over N color squared, which leads to the famous result, which is well known from the 60s in the quark model, that this is the result in the quark model, but you can translate it into the statement that the ratio of the neutron to proton magnetic moments is minus 2/3. And you can compare that with the experimental value of minus 0.68. And there's a whole host of other results. So this sort of combines chiral perturbation theory and the 1 over N expansion in a very nice way. Okay, the start of my headaches in EFT came with NRQCD or NRQED. So there's a whole series of papers, and again, a very big literature on this. But the basic idea is that if you take, for example, electrons and exchange a photon, or quarks and exchange a gluon in a non-relativistic system, you can approximate this by a contact interaction, which is the Coulomb potential. So you just write it as a dot. It's a 4 Fermi operator. And at low energies, low meaning small compared to the mass of the particle, you can treat it like a local interaction. Now, the problem has 3 scales in it. One, which is referred to in the literature as hard, which is the mass of the particle. Maybe you should just think of positronium or QED bound state. So this is the mass of the electron, a soft scale, which is the mass times the velocity, and an ultra soft scale of order the energy, which is mass times velocity squared. And the non-relativistic theory doesn't have pair production and all these other effects. So this scale's gone. But these 2 scales are still there in the EFT, and they talk to one another, and that's the source of the problem. So what the solution to that was, a solution we proposed was to label fields by the momentum value, P, and then have the Fourier transform of X be the energy. And if you do this, the Coulomb interaction, for example, can be written as a local operator like this, where this is the value of the 1 over R, the Fourier transform of 1 over R. And one of the things we realized was that when you start doing loop effects, you get 2 kinds of logarithms. You get logarithms of the energy. And when you do potential loops, you get logs of square root of 2me. And it's not possible to pick one mu to make both logs small at the same time. So we proposed a different way of doing the renormalization group, which is to do a renormalization group in velocity and introduce a scale m nu for the soft physics and a scale m nu squared for the ultra soft physics, and run in a correlated way in the sense that this runs twice as fast as that. And using this, Ian and I were able to calculate the alpha 8 log cubed alpha Lamb shift both in hydrogen and positronium, and this is the highest order calculation ever done in QED. So here's our formula, and also the higher alpha 7th log squared alpha hyperfine splittings. And at the time, there were 2 different calculations which differed from each other and for hydrogen, and we agreed with one of them, and this result has since been checked. And our method was also able to be applied to positronium because the renormalization group analysis didn't care whether we started with hydrogen or positronium. And this has not been done in the QED literature. And the correction we have is about 10 kilohertz to the Lamb shift, and that's relevant for comparison with experiment. Another thing we were able to do is calculate the Lamb shift in QCD, which has this ADM infrared divergence. But if you do NRQCD, the infrared divergence is not present anymore. And so we were able to calculate these diagrams and calculate the Lamb shift for QCD. The problem is that these labels that I mentioned somewhere back here and these correlated scales end up at some point causing a huge headache, which has lasted 20 years, and I haven't figured out a good way to solve it. So there's many successes, but the whole theory is, I'm not happy with the final formulation. There's a topic which is related to this, which I won't discuss in detail because I haven't worked on it, but Professor Weinberg started the theory of nuclear forces by doing NN potentials by pion exchange, and some of the same issues about soft regions and overlaps and so on come in, how to combine potential iterations and so on come in through diagrams like this in this problem as well. Another application of non-relativistic systems is NRGR, which Walter Goldberger will talk about, where the point particles in this case are solar mass black holes. And the new feature here is that you're doing loop diagrams in a QFT, but you're still doing classical physics. So there's classical pieces in loop diagrams, and you have to figure out how to extract them and calculate the gravitational potential between black holes. And this is relevant, for example, for LIGO and so on, where you need very accurate potentials to high order in the PN expansion. Lastly, I'll stop at soft-collinear theory, which is a theory for energetic particles, where you think of particles moving very fast, let's say back to back along the z-axis and the negative z-axis. And if you work out, let me not go through the power counting, but basically you have energetic particles whose off-shellness is much, much smaller. Lambda is the small parameter, is much, much smaller than the scale of the scattering. And again, this theory has fields with labels and multiple modes and suffers from some of the headaches of NRQCD, but things seem to be better here as far as the formalism concerned. This was originally used for BDKs, but now it's extensively applied to LHC processes. And next week's talk by Neuberg will be on application to Higgs physics. Okay, so now I want to discuss some things on recent work, so it'll focus mainly on stuff I've done. But okay, so first I'm going to discuss the extension of the standard model to SM-EFT. So this is really an old idea going back to the papers by Weinberg, Wilczek, and Z, where you think of adding higher dimension operators to the standard model. But the interest in the recent work has been to looking at baryon number and lepton number conserving operators and looking for deviations from the standard model at the LHC. And just classifying the operators took a long time. So from the original paper in 1986 to the final analysis in 2010 was whatever it is. I'm not going to be able to add in real time, but 24 years. And part of the reason was that there are equations of motion and field redefinitions you can make. And it took a long time to sort out what the complete independent basis of operators were. For 3 generations, there are 2,499 independent coefficients. So your effective theory has a lot of parameters in it. So the power counting of the EFT, if you work to dimension 6, is that the operators of dimension 6 run proportional to themselves. The standard model coefficients, just the usual QCD and QED couplings, etc., run proportional to themselves. This is the standard RGE of the standard model, but now you get new contributions which go like the Higgs mass squared times dimension 6. And this was missed in previous work. So we computed the entire anomalous dimension matrix for this 2,499 system, coefficient system. And there's some interesting features of the anomalous dimension which we found. So one of them is that there's a holomorphic structure to the anomalous dimension, even though, which is sort of reminiscent of supersymmetry, but the theory has no supersymmetry in it. And one consequence of this holomorphy I'll just mention is that, for example, the 3-gluon operator G cubed and the 3-gluon operator GG G dual have the same anomalous dimension, because they're related by holomorphy. One is the real and one is the imaginary part of a holomorphic operator. And if you start doing this diagrammatically, it's really quite mysterious because this operates as an epsilon symbol and many, the diagram structure looks completely different. We also found a lot of zeros in the mixing matrix where there was no reason for there to be zeros. And there's been some progress on understanding this based on amplitude methods and some recent papers over here. Okay, so then I wanted to discuss a little bit about recent work on extensions to the Higgs sector, because one of the experimental goals of the experimental program is to test the symmetry breaking sector of the standard model, the scalar sector, which is the one for which we have the least precise experimental information. So if you think of the Higgs, if you write the Higgs field down in this way, where you write the complex field in terms of each complex component in terms of two real components, you can assemble the Higgs field into a four-component real scalar field. And the standard model, Lagrangian, has an O4 symmetry where everything just depends on phi dot phi. And this is the famous O4 or custodial symmetry of the standard model, which leads to the relation MW is mz cosine theta. And so in extensions of the Higgs sector, I'm going to stick with theories which have an implicit O4 symmetry so that the theories have built-in custodial symmetry. It also makes the analysis much easier because we have an enhanced symmetry. Now, Higgs effective theory sort of arose from Technicolor, where you consider some kind of non-perturbative mechanism for breaking the symmetry. Now, the problem with Technicolor is that you don't have a Higgs particle. You only have the goldstones from the symmetry breaking, which get eaten by the W and Z. And because the Higgs was found to be light, Higgs effective theories basically add in an additional light scalar field to the dynamics. So just the difference between the two in some schematic way is that in the Higgs effective theory, we have the Higgs particle, and I'll call this a vector n, which are the goldstone bosons of the interaction. And in the standard model effective theory, what you do is you take this four-component field and write it as a magnitude, which is v plus h, and a direction n. So this n here and this n and the two are the same. But in the standard model effective theory, the radial direction has a very precise form connected with the magnitude of that four vector. Whereas in the Higgs effective theory, you kind of peel off the radius and treat it like an independent variable. So you can unify both approaches by just thinking of the scalar field of the standard model as living on some scalar manifold with a metric and some kind of kinetic term like this, where the indices I run over the 3 pion degrees of freedom, or what I called n hat before, and the radial direction, which is the Higgs field. And we're living at this black dot here, where the symmetry has been broken by the vacuum expectation value, and our experiments are probing some local neighborhood of this point. So what can we do experimentally? So what we did was we realized that in a quantum field theory, we know that the S matrix is unchanged under field redefinitions. Amplitudes can change, but the S matrix remains the same. The geometrical properties of a manifold are independent of the coordinate parameterizations. So what we're trying to do was to write observables in terms of geometric quantities. So we can write all the experimentally measured quantities in terms of geometric invariance of the manifold. And the first invariant you have on a manifold is the Riemann curvature tensor. And so you should be able to write the scattering amplitudes in terms of the Riemann curvature tensor. So just to explain the next formula, the Riemann curvature tensor has a whole bunch of indices on it. And so it's convenient to consider sectional curvatures, which take a two-plane labeled by x and y. X and y are perpendicular unit directions, and you just contract r with these unit vectors. So you get the sectional curvature in the xy plane. And our theory has two independent sectional curvatures because the pion directions are all equivalent. We have k pi pi, where two of the vectors are pionic. Remember that 3 pion directions. And k pi h, where one direction is pionic and one is h in the Higgs direction. And if you tried two Higgs directions because of the anti-symmetry of Riemann, this would just vanish. So what we found was that if you look at the high energy behavior of scattering amplitudes like WW scattering, etc., there's the standard model piece. I've just written a simple form in the limit that the gauge coupling is small. But then you get terms which grow with energy, and they depend only on curvature invariance. And if you look at the Higgs effective theory literature, various people have different models, and they all calculate these high energy behavior of the scattering amplitudes, but all their formula are actually the same formula. You just calculate the curvature of the Higgs effective theory manifold they're using, and this is a universal formula for all of them. And the scale of new physics is given by the mass of these is the point at which this term gets bigger than 4 pi. And so the scale of new physics, I should have used capital M here, is 4 pi over the square root of this curvature. So what the LHC can probe is essentially the curvature of the scalar manifold. In the standard model, it's flat. In more general theories, it's not. And you can go measure the curvature by looking for these deviations from the standard model scattering. Now, there's one interesting feature of composite Higgs models which depend on G mod H sigma models, which is that in any G mod H space, all the sectional curvatures are positive. So we actually have a sign result. That is, these terms have a specific sign. We investigated some models on a hyperbolic manifold, but I won't get into that here. How am I doing for time? Okay. So I rushed through a little bit, but I wanted to discuss a couple of things which people are doing, which are kind of interesting. And this is very recent work. So there are certain unitarity bounds one can get on EFT coefficients. And the basic idea is actually quite old. It comes from pi-pi scattering, where you essentially write down something analogous to dispersion relation. So here, for example, in the pi-pi scattering, in the S-plane at fixed t, there's a branch cut on one side, and there's another branch cut, the U-channel cut on the other side. And suppose I look at a point here, I can take a little contour around there and use Cauchy's theorem by, okay, let me try writing with my pointer, but you basically go, dz over z minus z naught to f of, okay, things disappearing times f of z will give you the value of f of z naught. So you write it as a contour integral over here, and you deform the contour into this big contour on the right-hand side. And so the assumptions are the contour at infinity doesn't play a role. So you get two cuts. You get the discontinuity across the two cuts, and the two cuts are, the discontinuity across a cut is a cross-section, and we know cross-sections are positive. So you get some formula for the amplitude here in terms of some integrals, and for certain amplitudes, because the cross sections are positive, you know that the value here is positive. Now, you can pick this value very close to the origin where your EFT should be valid, so you can calculate this amplitude in terms of EFT coefficients. So this gives you some inequality on certain combinations of standard model EFT coefficients. You can just think of it as an inequality like some C is bigger than 0. And so people are investigating this, and there's some interplay between high energy physics and low energy physics, which is sort of interesting here. One thing which I've been working on is the Coleman-Weinberg effective potential. And it turns out that we can use the EFT method to renormalization group improve the Coleman-Weinberg potential and some of the leading log series. And you might think that this should have been done in the 1980s, but it turns out, as far as I can tell, it hasn't been done properly. And so we figured out how to do it, and should have a paper out pretty soon. So Mike wanted me to sort of give an overview. So if you want to learn more about the subject, there was a Lesuche summer school in 2017 called Effective Field Theories in Particle Physics and Cosmology, and these are the editors. And probably all the lectures are, I didn't check, but most of the lectures should be available on archive.org, so you can look at it. One thing I didn't talk about, or two things I didn't talk about, are applications to cosmology, and there are some nice lectures which are in this volume discussing inflationary cosmology and large-scale structure. So, of course, there's going to be tons of discussion in the future talks in this series.